All right, guys, we're back again. This is Justin from chemistrynotes.com, and in section 14, we're talking about acids and bases. This is our second video from section 14, and in our first video, we introduced acids and bases. I talked about the Arrhenius acid and base definitions. Then we focused primarily on Bronsted-Lowry acids and Bronsted-Lowry bases, conjugate acid-base pairs, and I want to continue with Bronsted-Lowry acids right now. Then we'll do some simple dissociation reaction practice, and then we'll finish off this video with a discussion of acid strength. So in this example, I have NH3 gas plus HCl gas, and if I look at my product, NH4Cl, that is an ionic compound, right? So technically I can break up my NH4Cl into a cation and an anion. And if I do that, it's easier for me to see the conjugate acid and conjugate base pairs. So what's going on in that boxed up equation? Well, NH3 is becoming NH4 plus. So NH3 must be my H plus acceptor. Now, he's not sitting around waiting for it. He goes out and grabs it from HCl. If you look at my arrows there, and then the bond between H and Cl goes on to Cl to make another lone pair on Cl for 4 lone pairs, and that's Cl minus. So HCl is my H plus donor. He's donating an H plus ion or a proton to NH3, and we get NH4 plus, which is the conjugate acid of my NH3 base. And we also have Cl minus, which is my conjugate base of HCl. All right, so that's it for Bronsted-Lowry acids. I mean, it's not it, but it's it for now. Let's do this example. Simple dissociation reactions. This is where you are given an acid and you simply break it up into its ions. What do I mean? You take an acid like we did in A for acetic acid, HC2H3O2, and then donate the H plus. So let's look at B here, H2SO4. Let's donate an H plus. So what do I get? I get H plus aqueous, that's my proton that's been donated, plus what's left? HSO4 minus. Now in C, it's a little crazy looking, but you know that a simple acid dissociation reaction is when you pop out or you release or donate, keyword donate an H plus. So my product has to be, the first product is H plus. Then I just write what's left. So instead of AlH2O6 3 plus, what's left? AlH2O5 OH, and now my total charge for that is 2 plus. Okay, that's a complex ion. We'll talk more about that in section 18, way down the line. All right, let's finish off with acid strength. Here is my reaction that we've seen before. It's a general acid reacting or dissolving in water. HA, or I should say reacting with water in this case. But HA is my acid, right? And it's reacting with H2O. Water's acting as a base because it's accepting or receiving or gaining an H plus. How do I know? Well, just look at the product. It's H3O plus, right? So if that acid, HA, is a strong acid, it's going to have a weak conjugate base. Okay, that's the new, and you should commit that to memory. Strong acids have relatively weak conjugate bases. Okay, strong acids have Ka values that are very large. So equilibrium lies to the right. Remember, Ka is products over reactants. So if Ka is large, that product's concentration would be quote unquote large. Now, if HA is a weak acid, it's the opposite. A weak acid has a relatively strong conjugate base. If it's a weak acid, it's going to have a Ka value that's relatively or quite small. If it's small, equilibrium is going to lie towards the left. Okay? Why does it lie towards the left? Well, if it's a weak acid, it's not all that good at donating its H plus and causing a reaction to go towards the right, towards products, right? So I'm going to go ahead and draw out a table here just of some acids that I wanted to include. And this we'll call this table 14.1 since we're in section 14, acids and bases. And this table is going to show Ka values all right, acid dissociation constant, Ka, values for some common monoprotic acids. And monoprotic just means it has one acidic H plus that it can donate. All right. So on the left-hand column, I'll write the name of the acid. I'm sorry, the formula of the acid. And on the right-hand column, I'll give you the Ka value. HSO4 minus 1.2 times 10 to the minus 2. HClO2 1.2 times 10 to the minus 2. HC2H2ClO2 1.35 times 10 to the minus 3. HF 7.2 times 10 to the minus 4. You see how my Ka values are getting smaller as I go down? That means the strongest acid is going to be at the top. The largest Ka value I've shown in my table is HSO4 minus. All the way down at the bottom here, we got guys like HCN with a Ka of only 6.2 times 10 to the minus 10th. And NH4 plus is a little out of order there, 5.6 times 10 to the minus 10th. And the last one, HOC6H5, 1.6 times 10 to the minus 10th. So in my table that I've just drawn using some of the acids I wanted to use, HOC6H5 down at the bottom, that's my weakest acid. HSO4 minus is my strongest acid. And when I say strong acid, I mean relative to the others in this table. The real strong acids, and look at my side note here, the actually quote unquote strong acids like hydrochloric, like nitric, like perchloric, like sulfuric acids, those four, HCl, HNO3, HClO4, H2SO4, which is diprotic, by the way, can donate 2 protons. They're not even listed because their Ka values are so extremely large that they're off the charts. Okay. All right, so let's finish up with a sample problem. Now, on the last page, you saw table 14.1, and that was a list of my particular acids that I wanted to show. And it had the Ka values listed so that the top was the strongest acid and the bottom was the weakest acid in my list. Now, this sample problem is telling us to use that table of acid strength, but then they're asking us about bases. So it says, using table 14.1 on the previous page, arrange the following bases from strongest to weakest base. Well, how the heck can I use an acid strength table? Well, remember what I said? The strongest acids have the weakest conjugate base. The weakest acids will have the strongest conjugate base. So let's just figure out what the conjugate acids are of all these guys, okay? So underneath each squiggly arrow, F minus, conjugate acid is HF. Cl minus, the conjugate acid is HCl. NO2 minus, HNO2 is the conjugate acid. And then HCN is the conjugate acid of Cn minus. So the weakest base is the conjugate of the strongest acid. More importantly for this particular problem, the strongest base is the conjugate of the weakest acid. So who is the weakest acid up there? HF, HCl, HNO2, or HCN? Well, the weakest acid of the group is HCN. Well, in that case, Cn minus, the conjugate, must be the strongest conjugate base. Cn minus is the strongest base. HCl is the #1 strongest acid on there, right? So that means Cn minus is my weakest conjugate base, and then you can put together the list as such, okay? Stronger acids, weaker conjugate bases. Weaker acids, stronger conjugate bases. All right, in the next video, we're going to talk a little bit more about water. So far, we've been using water as a base, right, when it reacts with HA. Water can also act as an acid, and it's said to be amphoteric. NH3 is also amphoteric, and we'll talk about these in the next video. So if you like the way I do these handwritten chemistry notes, I have full course general chemistry and full course organic chemistry notes. You can get them all at chemistrynotes.com. And stick around for video number 3 from section 14. It's coming up right now.